So, our first law, does anyone remember what that one was about? Rachel does.
Isn't that inertia?
It's all about inertia, right? That's kind of the key word, inertia. Or basically, if we've heard kind of, you know, the famous saying, an object at rest will stay at rest, and an object in motion will stay in motion unless it interacts with another force. And inertia is explaining that, like, an object wants to retain its inertia. So it wants to keep moving. So, in your take-home quiz, that is now actually your assignment, so let's get out your take-home quiz and talk about one of the examples. Some of you had already handed it in, like Morgan, Kim, Dylan, and Hannah should come get yours. So, to clarify a question from your assignment, so let's look at number 3. When riding along in a muscle car, the driver steps on the accelerator and you're thrust back into your seat. So, let's think about it. Let's say that the vehicle was going at, say, 56 kilometers an hour. That means your body and the car are going at 56 kilometers an hour. If the car puts on the accelerator, now the car is, say, going 100 kilometers an hour. What was your body going? 56, according to our situation, right? Our body was going 56. So, an object in motion wants to stay in motion at the same magnitude and direction. So your body wants to stay at 56 kilometers going that way. If the car that you're in starts going faster, you're still slow, right? You're still 56 kilometers an hour, so you got thrust back, right? Because the car's going faster now. So what law is that? First one. So that's Newton's first law. So that's because your body, write a note into yourself there, or the person, or your body wants to stay at the same velocity it was originally going. So an object in motion will stay in motion at its same vector, so same direction and magnitude. Okay, then we did, well, actually first we did Newton's second law. What's our formula for Newton's second law, Lisa?
Good question. F net over M equals A.
F equals M, or F net equals M over A, or F equals M times A.
F over M equals A. So it's not the same thing?
Yes,
F equals M.
just rearranged. So F net equals M times by A, or Lisa said, you said F net over M equals A. Yeah, so just same thing, just rearranged. And I believe it's this one that's on your formula sheet, is that correct? I think so. Yeah, so this is the one that's on your formula sheet. So remember, you need to know how to rearrange these things. Now, let's just make a note so that we remember what units these were all in, because it was super important that they stay in the units they're supposed to be in. So F net, what are my units, Aiden, for F net force? Newtons. And mass, Dylan? Kilograms. And our acceleration is meters per second squared. There was one other formula that we used in Newton's second law, but we applied it specifically to gravity. So what was that one, Addison? What was our specific one?
G equals over A.
So let's just put Fg for the force of gravity, and we have mass. And instead of writing A for acceleration, we say it's the acceleration due to gravity, so we put a G in. Yeah. And we know that G is equal to 9.81 meters per second squared. Okay. Then the third law, this was all about how objects interact with each other, okay? So this is all about object interactions. For every action, there is what?
Reaction.
There is, can we say something more specific about the reaction? An equal and opposite reaction. So let's just specify a couple things about this type of reaction. So let's actually classify what is the action force. So action force is the force initiated by object A on object B. Then the reaction force is the force exerted by object B on object A. Then we made the mathematical assumption that F action is equal to negative F reaction. Now, this only means the forces happening, being basically the action of a force and the reaction of the force, are the equal and opposite. That is not in reference to acceleration. Okay? Say we think about a rocket. We made the assumption that F of the gases of a rocket is equal and opposite to the F net of the spaceship going up. But are their accelerations necessarily the same? So I'll just do it. Let's go back to our assignment and look at number 5. So this one was kind of a tricky one because it was worded a little bit differently, so let's work through it together. So it says the exhaust gases and the spaceship will accelerate in opposite directions. So I'm going to just make, oh, right. Well, I have my spaceship, and all of the gases are pushing the spaceship up. So, my spaceship is going up and the gases are pushing down. Okay? They're accelerating in opposite directions. Is the force equal and opposite? Yeah, we just made that assumption, right? We say the forces are always equal and opposite. For every reaction, the force is equal and opposite of the reaction. But is this asking about forces? No, it's asking about acceleration. What do we know about acceleration? Well, the formula that we did for acceleration is F is equal to m times a. So if the forces are the same, so say I have force of my rocket is equal to m times a, and force of my gases is equal to m times a, these F's are the same. Is the mass of the rocket and the gases the same? Heck no. A spaceship is way heavier than like a bunch of hydrogen gas, right? Yes? Maybe? Giant spaceship made of lots of metal, okay, is way heavier than a bunch of gas. So is the A going to be the same? No. If the F's are the same and we have different masses, their accelerations will be different. Okay? So this one was hard because of the wording, right? So their acceleration, they accelerate in opposite directions with what? Different or same magnitudes? Different. This is according to what law? What law is this?
The third